Hey guys, hope you had a good spring break. We're gonna start the next unit similarly to how we did the review for Newton's laws, where I'm gonna show you a pre-recorded session that's now. And then in a little bit, I will open up a Google Hangout where we'll do a little more interactive piece, which will come at the end of this so that you guys will have a few minutes to think about what you want your answers to be before you enter the little more open format Hangout. Give me a second. I just got to present my screen and I'll go through a couple slides on our next unit, which is thermal energy transfer. Okay, so you should see hopefully 3 types of heat transfer. And I'm just going to put it in present mode so that it's a little bit clearer for you to see. Once it starts loading, I'll start going over them. Heat transfer is something that you guys talked about probably in, I want to say 6th grade, when you talked about the different sorts of shifts in tectonic plates, particularly with volcanoes and weather. But we're going to get a little more involved in it this year because you know more about molecules and their movement. So the 3 types of heat transfer, if you don't remember, are convection, conduction, and radiation. So first, thermal energy is something that we talked about as one of the energy types when we were doing our Rube Goldberg machines. And we didn't really talk too much about what it actually meant other than identifying it as mostly a part of something generated by friction. But thermal energy is the energy side of things, but heat is thermal energy that's actually being transferred from one place to the other. A lot of times when we use the word heat, we think of it as something that's hot, but it can be either hot or cold, because you got to remember that heat is actually the description of the transfer from one place to another. So, like, for example, if you put your hand on the table and you feel that it's cold, that's actually just your brain indicating to you that the heat from your hand is moving away from your hand onto the table. And that's why your brain says, ding, 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 the table's cold, even though it's actually like, my house is 66 degrees right now. It's not too terribly cold. So what is thermal energy? All matter is made of tiny particles that cannot be seen with the naked eye. These particles are always in motion, and motion is a form of energy, like we've already learned. An object's thermal energy equals the total energy of all its moving particles. So I'll put a little diagram up in a second of how we shift from one state of matter to the other, but hopefully you know and or remember that as you move to something that from a solid to a liquid to a gas, there's more and more energy in the molecules that are in that object. And that would also describe more and more thermal energy. Heat transfer happens when some of its energy moves from one object to another, and it happens in one of 3 ways. So heat always, always, always flows from hot to cold. So for example, if you are lucky enough to have central air in your house, which I just moved last year and I finally do, which is awesome. But you know, in the summer, your house gets really, really hot because it naturally, the hot air outside heats the air inside your house. And you have to actually apply a large amount of energy to be able to make heat transfer the opposite direction. And that's what an air conditioner does. It uses energy to force the opposite reaction to happen. So why does an ice cube melt when you hold it in your hand? How does the energy actually flow? So the ice cube actually doesn't make your hand cold. So a lot of times you think of it like that because after you hold an ice cube, hey, your hand's cold. But in actuality, because of the natural flow of heat, your hand is heating the ice cube. So your hand is making the ice cube melt. And as a result, the heat that was, or the thermal energy that was in your hand has been conducted by direct contact to the ice cube. So if you look at the diagram here, heat is always going to flow from hot to cold, and it'll do so in 3 different ways. And they're pretty different from one another, although a lot of times more than one is happening at the same time. So you have conduction, convection, or radiation. And obviously, we're going to go into the difference between those next. So just a recap for particle movement in the different states of matter. I think I've kind of given this scenario before in class earlier in the year when we were dealing with more chemistry, but as you increase the thermal energy of molecules, the substance can change state. So if you have a solid, it would be similar to like if you think of our classrooms and we're all sitting in kind of uniform rows in our desks. People are kind of shimmying around in their seats, but nobody's really getting up and moving past each other, at least not significantly. And now we shift to a liquid. Now the same molecules are in the room, but now we're moving around to the lab stations or we're doing a lab and there's more movement. People can walk past each other pretty freely. They're taking up a little more space in the room. And then we shift to a gas and I say, hey guys, we're at our lab stations. Now let's play dodgeball. There's a lot more energy involved in that case and some comedy and hopefully picturing that happening in our classroom because I miss being there. The first type that we'll go over is convection. So heat transfer caused by the rising of hotter, less dense fluids and the falling of cooler, denser fluids. So I'm going to go back to the last slide for a second because if you look at the gas slide here, you can see that the molecules, there's the same amount of molecules that are there, but they're much more spread out. And when they're more spread out over a larger volume, they are going to have a lower density. And when things have a lower density, they float up, like a helium balloon will rise up in the room. But if you just blow it up with your breath, it's not going to rise up. So as things heat up and they spread out more, the density lowers, which causes them to rise up. And that's the whole idea of convection. So if you think of a pan of water or the molten material in Earth's mantle, which is probably the last time you learned convection, they all heat in the same way. I often picture it as if you ever made spaghetti, you can actually see the convection currents if you let the spaghetti like come to a really, really hard boil. So at the bottom of the pan, that water is going to heat up first because it's closest to the heat source, the stovetop. And then once that heats, it's going to rise up because the molecules are spreading out. But as it gets closer to the surface of the pot, the air that's outside the pot is going to start to cool, or the heat's going to transfer away and the top pasta will actually cool down. And once it cools down, the density lowers and then it's going to sink again. Well, and then once it sinks to the bottom, it gets closer to the heat source again and rises up, and hence a convection current is born. If you look at the left side of the screen, you see that the sun heats the Earth's surface, which heats the air above the ground, causing the air to rise. And as it rises, the air cools and sinks back to the ground. That's really the majority of what creates most wind. There's also some other factors involved in that, but a lot of it is just the heating and cooling of the air in the Earth's surface. The next one is conduction. This is probably the easiest one because it's always just direct contact of any form of molecules. One thing that I will point out now is that the last one is obviously the movement of molecules. Lower density rises and greater density sinks. But that requires molecules. So does conduction. So conduction is a transfer of thermal energy that happens when particles collide with each other. It can happen in solids, liquids, and gases. When two substances of different temperatures touch, molecules are required. So the burner, if it's directly on like an electric burner, then the transfers heat to the pan gets hot, the bottom of the pan gets hot before the pan's handle, and then the burner's heat vibrates the particles in the bottom of the pan. It's like a domino effect. So kind of picture, so say we're back in our classroom. You can tell obviously that I'm feeling homesick from D112. But say we packed all 120 of us in that room. We would be pretty much shoulder to shoulder, very little room. So now I want to play a practical joke on everybody, and I stand in the front corner of the room by where my lab coat always is, and I just decide to push. For David, I throw some elbows. So I push, and eventually at the back corner of the room, or maybe slightly before them if the energy depends on how aggressive I am, it's like a domino effect. It'll hit the next one, the next one, the next one. And that's really what conduction is. The heat source happens somewhere, and then it's a domino effect that that eventually leads to somewhere else. Good conductors are materials that are going to do that really, really, really easily. It's usually things that are dense because the molecules are closer to one another. So for one to impact the other is a lot easier. You can kind of think of it from your Rube Goldberg projects. A lot of you had some sort of domino effect. And if you actually physically had dominoes, you know that it got really frustrating if you accidentally placed two dominoes just too far apart so that the one couldn't actually hit into the other one. And that would be where the conduction would stop because there would be no direct contact available. That's kind of the idea of insulators. It's a material that will really slow the transfer of thermal energy. Now, there's no perfect insulator, so you can't completely stop the transfer of energy. If you're wearing a down coat, if you're in Antarctica, eventually you're still going to get cold, but it's just going to take a lot longer to do that. You can think of it if you're outside playing in the snow and you first go out and you're nice and toasty warm, and then you're out there for like an hour and a half, and all of a sudden you can't feel your toes and your hands, and it's not because they got wet from trampling around in the snow. But insulators are usually less dense materials. Like think of a puffy down jacket that's super light, but it prevents that kind of domino effect from happening like wood happens so effectively in a conductor. The last is radiation, and this is one that you probably didn't really talk about or it was just mentioned in the past because you really have to know about energy transfer for this. One of the next units that we're going to do is on the electromagnetic spectrum and how waves travel. But the key here is that this is the transfer of energy by the movement of electromagnetic waves or subatomic particles, but radiation can actually happen with no molecules present. And it is the only type of thermal energy transfer that happens with no direct contact of any molecules. So I'm going to repeat that again because it will be a test question at some point. It will come up now time and time again. But radiation does not require molecules. That's the only reason why the Earth can actually be heated from the sun, because there's areas from the sun to us on Earth that are completely empty, no molecules, no anything. So you can't have a domino effect of one molecule hitting the next molecule hitting the next because there are none. So the only way that heat can actually end up getting to us is by radiation. We tend to think of radiation as this Hulk smash kind of weird gamma radiation effect, but radiation can be simply just heat, a specific type, which we'll talk about here. So say you're sitting in front of a fire from a fireplace. Now, if you're hovering above the fireplace, like you're out and in your backyard and you have a fire pit, sometimes the heat can just rise through the air, and then that's convection. But if you're actually standing directly next to or in front of the flames, like say sitting in your house in front of a fireplace, that's not heat rising. You're right out in front of it. So the only way that that's actually getting to you is via radiation and maybe a little bit of conduction through the air molecules, but much more rapidly the radiation. Sunlight can be felt from 93 million miles away, more than 93 miles. Microwave ovens use it to cook food. It's a little bit different form. There is some, it's called infrared radiation is what we're talking about now. But microwaves are a little bit higher energy level than infrared. And once we talk about the electromagnetic spectrum, that'll become more clear. And then when you get even higher on the radiation spectrum, you get to ones that it can actually kill germs and cancer cells, which are like ultraviolet and gamma radiation. But that's not the infrared radiation that we're going to be talking about for these three energy types for thermal energy in particular. Okay, so I'm going to leave this up on the screen just for a couple seconds and talk about it a little bit, because this is the kind of thing that you're going to need to be able to do ultimately with convection, conduction, and radiation to be able to prove to us that you understand the three different types and applying them to just a random scenario. So at the end of this pre-recorded lesson, I'm going to be posting a couple things. I'm going to be posting a Google Hangout that you'll be able to join. And then I'm also going to be posting this picture. So I'm going to give you probably, I don't know, you're probably going to end up with a